This is our follow-up lesson for 5.3. It's 5.3 part 2, and in theory it's going to be a shorter lesson. It's just going to be a little more involved, and we're going to use some graphing calculator work today. So first, this is a review of what we did yesterday on more basic equation solving for trig. So I look first for the fact that, okay, I have what kind of is like resembling a polynomial in the fact that there's terms, and we have a common term of cosine. So let's factor the cosine out of that expression, and then we still have sine minus 3. And then if we treat this with the zero property that we learned back in polynomials, I set each of those factors equal to 0. I want to know when the cosine is 0 and when the sine of x minus 3 is 0. And they do want me to solve for all values, so we have to do that weird rotation. Alright, so if I look at my unit circle to start with, when is cosine 0, that would be at pi over 2 and at 3 pi over 2. And then sine of x equals 3, well, don't think about that too hard, guys. The sine of x is bound between -1 and 1, so it's not going to equal 3. So think about your unit circle here, guys. We're talking pi over 2 and 3 pi over 2. So if you wrote down, oops, pi over 2 plus and minus 2 pi n, and then you wrote 3 pi over 2 plus and minus 2 pi n, I don't have a problem with those answers because I understand what you're saying. But what you're really just doing is you're starting at pi over 2, and you're adding a half rotation, so you're adding a pi. So this is really the simplest way, you can say plus and minus, the simplest way to write our answer. There's other ways. I think that's the simplest way. Alright, moving on. Again, don't get hung up on is it the simplest way or not. If you can't come up with the simplest way, I'm okay with that. Alright, in this question, our issue is we have cosine and sine functions and we can't factor anything out. So what we're going to have to end up doing is trading. So I look for Pythagorean trades, cosine squared. I could easily trade for a 1 minus sine squared. And I don't really need the parentheses here because you have the rest of this. Nothing's being distributed, but what I do notice is I have, looks like a quadratic looking thing. So the 1 and this 1 will join together, negative sine x, sine squared, excuse me, x, plus sine x, and then 1 plus 1 is plus 2. So I'm going to kind of factor this, but I don't like that this is a negative. So if we switch everybody's sign, this becomes sine squared x minus sine x minus 2. And then this really closely resembles this sort of a quadratic that I would factor and solve. So using that same factoring technique, sine squared would be sine times sine. And then my back numbers are going to have to multiply to -2. The arches, if you want to call them that, are going to add up to -1. So what if I did a minus 2 and a plus 1? Because that would be minus 2 plus 1. Yeah, that would work. So this function, if I set it equal to 0, would be sine x equals -1. And this function set equal to 0 would be sine x equals 2. So we have another one of those cases where I can ignore that completely because that's not going to happen. And then when is sine -1? That would be at 3 pi over 2, right? And they want, for all values of x, so 3 pi over 2 plus and minus 2 pi n. Again, remember, if you're looking at my notes, for some reason I used k instead of n. Old habits die hard and all that. I had a professor in college that would only use k for all integers, no matter what problems we were doing, so I had to work with it. Sorry. Alright, we're back. So tangent, secant, I can't handle those various functions within the same equation. So let's trade tangent out for, excuse me. Oh gosh, I always forget this one. Let me cheat for a minute. Find my paper. What is tangent? Tangent, oh, secant squared minus 1. That would be perfect, because then we'll have all secants. Because then we have a plus secant over here. We have another minus 1 here. So we do have what's resembling like a quadratic that we're going to factor. So we have secant squared, and then a plus secant, and then a minus 2 when I collect those ones together. So this is a great candidate for factoring. Secant times secant will get us secant squared. And then, let's see, it has to add up to 1. So let's make that 2 positive and the 1 negative. And if we solve both of these, secant of x equals 1, and the secant of x equals -2. But remember, secant is not on our unit circle so much, it's the reciprocal of cosine. So the cosine reciprocal of 1 is still a 1, but here the cosine would be a -1/2 if I look at the reciprocal. So they want all solutions just on one rotation of the unit circle. All right, let's start listing. Cosine of 1 would be 0. And that's it. And then cosine of -1/2 would be, I'm going to cheat, I already wrote these down somewhere, 2 pi over 3 and 4 pi over 3. That would be from quadrants 2 and 3. All right, and that's all we had to do for that question. Oh, I should have triple checked that tangent wasn't undefined. 0, tangent is not undefined, so yeah, we're good. All right, and it did say to check all solutions by graphing. I'm going to skip that for time. I was interrupted by a couple of people here, so my planning hours kind of shot. All right, here, again, we're going to want to graph to check all solutions in theory, but I'm not going to have time to do that. So, between 0 and 2 pi only. Oh, bummer. Not real happy about the fact that there's sine and cosine. So what if we were to square both sides of the equation? That's something we can do, right? So this becomes 1 plus 2 cosine squared x. Nope, back up. 2 cosine x plus cosine squared. And then square root of 3 squared is still 3, and then, whoops, oh my gosh, sine squared x. And then remember, we don't want sines and cosines, so what if we traded this sine squared out for 1 minus cosine squared? That would work perfectly, right? So we have 1 plus 2 cosine x plus cosine squared x equals, let's distribute that 3 that's in front of here, so 3 minus 3 cosine squared x. Yuck! Resembling what's going to be, I think, a factoring question. So let's bring everything to one side. I'm going to add this guy over. I'm going to subtract this guy over. 3 cosine squared. Subtracted this 3 over. Oh my goodness. All right. And then doing a little rearranging, I'm going to put all the cosine squareds first. So 4 cosine squared x plus 2 cosine x, and then 1 minus 3 is a minus 2. And I'm going to do everything I can to make my life easier. So if I divide everything here by a 2, or multiply everything by a 1/2, at least it gives me some smaller numbers to work with. So 2 cosine squared plus cosine minus 1. Alright, that's not too bad to factor. Alright, 2 cosine squared would be 2 cosine cosine. And then I need my factors and the end to multiply to -1. I need the, oh, what was that? You just said 2 cosine cosine and you wrote down 2, 2. Right, this is cosine. So what if we made, let's see, this a plus 1 and this a minus 1? Because that would be positive 2 minus 1, which will give me positive cosine in the middle. Yeah. And again, if you're not so comfy with that factoring, change it out for x's instead of cosines. And think about how you would have factored that trinomial. It's the same idea. Alright, so setting each of these equal to 0, this one gives you cosine x is 1/2 when you solve it, and this one says cosine is -1 when you solve it. So, we have to start listing out those, and I'm going to cheat. Maybe. Alright, cosine -1. That would be at pi. And then cosine of 1/2. Pi over 3. And 5. I feel like I'm missing. Oh yeah, quadrant 4. 5 pi over 3. And this is kind of interesting because, you know, we don't see anything wrong with this, but when we graph it on the calculator, when I type this into y1 and this into y2, and I set my domain to go from 0 to 2 pi, turns out that that one doesn't work. We can investigate algebraically why it doesn't work, but for now, let's just trust that the calculator is going to tell you when something doesn't work, and it's a good double check. P.S. If on a test, if I say graph and check or graph to find your solutions, like, you need to do that because something fishy might be going on. All right, here, they're going to have you on your calculator type one side of the equation into y1. So we're going to type this guy into y1, and then this guy into y2. And we're going to set our domain, our x min and our x max to 0 and 2 pi. So pause the video and get this all typed in. I already did, so let's take a look here. And make sure you're in radian mode before you graph. I set my range, I think, -1 to 1. And I can see that these functions are intersecting in two places. So we're going to find the intersection point by using our calc menu and choosing the intersect feature. And then when you enter, 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 it's going to default to the closest intersection point. So we're going to write down 3.9584. I forgot what it said to round to. And we're going to do that again. But this time, when you hit enter the third time, before you hit enter the third time, you need to get closer to the other intersection point. Otherwise, it's going to keep finding the same one over and over again. So 5.466, whatever they wanted us to round to. Alright, it does say solve, find the first solution, use your knowledge of symmetry, yada yada, period. Okay, so lovely. As always, Abruzzo, very good. Alright, so this ordered pair here, that intersection point was, what was it, 3.9, blah, blah, blah. Okay, and this guy here was 5.46, blah, blah, blah. And they want you to think about symmetry and what's going to happen here. So, if you, this is a little confusing, right? Go back to your algebra instincts. In order to solve for sine, we would have applied the inverse sine function to that negative decimal, negative 0.729. And on your calculator, it tells you that x equals negative 0.816 something, something, something. So, according to your calculator, this is the solution, where this red line would have crossed back here. But remember, they wanted all solutions between 0 and 2 pi because of this domain restriction. So what's happening is it's... back this up a little bit. Okay. What's happening is it's taking pi and it's backing it up, or adding to it this 0.816 little tiny decimal here, or 2 pi I should say. So if you take 2 pi and you add to it or subtract from it this 0.816 decimal, you get this number right here. Okay? And then if you do the same thing with pi and you add that little tiny decimal, you get that. Okay. So what we're going to notice is that they wanted us to write all solutions. There's a few different ways we could write this. Let's see. I think what I'm going to write is, there's a bunch of different ways we could write this, huh? How about we write 3, does it want all solutions? Let's back up a minute. Well, we know the period for sine is 2 pi, right? So I would be okay if you just took this number and said plus and minus 2 pi k, and then same thing with this number. That would be okay. But what I want us to recognize is that where this number came from was simply the 0.816 decimal added some pi. So there's other alternative ways to write this. I'm not gonna test you on that. Sorry. Interrupted again. Oh, Abruzzo, just keep reading, girl. Number 6. They want all solutions this time. So the way I'd like you to write it is what we originally talked about. Take this 3.9, let me write the rest of it, 585 decimal, and then just say plus and minus 2 pi n. And then same thing with the 5.4663. Don't try to get fancy. But it is nice to know that where this number is coming from and where this number is coming from is directly related to the inverse sine value that your calculator is going to be giving you. So it's not like it's some big mystery of these numbers are coming from, you know, space or magic. They have mathematical appropriateness to them. this next one we would solve on our calculator as well. For the sake of time, if you don't mind, I'm going to have to just kind of put a kibosh on this. But we need to talk about this because this is different. All right, this is called u-substitution. So before we talk about double angle problems, we have to realize that inside the sine function, you might have something other than just x. Like for instance here, you have 2x. So what you're going to do is you're going to replace this with, we'll call it u because that's the easiest for us. And off to the side, I'm going to remind myself that u is really a 2x. So when I figure out where the sine function is negative square root of 3 over 2 within 0 to 2 pi, I look at my unit circle, and I find the answer to that to be, I'm going to cheat for a minute, 2 pi over 3 and 5 pi over 3, right? So this is what's kind of confusing. Because this is u, we actually have to do this question first, where we have to find all solutions. So do that for me, please. Set up u equals 2 pi over 3 and u equals 5 pi over 3. But all solutions means that you would add this 2 pi n or 2 pi k. I think my notes say 2 pi k, so don't panic. But remember, u is not what we're actually solving for. What we're really solving for is x. U was 2x. So if I think about how am I going to solve that, I'm going to divide everything here by a 2. So divide by 2. If you divide this by 2, you just increase the denominator by 2. Same thing here. Same thing here. Same thing here. All right. So what you end up with is x equals 2 pi over 2 times 3. The 2's would cancel. So pi over 3 plus the 2's would cancel, pi n. And then here, you would get, let's see, 5 pi over 6 plus pi n. You actually have to find the all solutions one first, and then come back to this guy. Because I actually don't want this. If they just want all your answers between 0 and 2 pi, what you're going to do now is just start plugging in integers for n until you reach the end of your domain, which is 2 pi. So, pi over 3, good answer. If I plug in a 1 for n, so pi over 3 plus pi would be 1 pi over 3 plus 3 pi over 3, that's 4 pi over 3. And then adding another 3 pi over 3 would be 7 pi over 3. But, you know, that's over 2 pi, so let's not do that one anymore. Alright, 5 pi over 6 plus 6 pi over 6 is 11 pi over 6. So 5 pi over 6 is good. 11 pi over 6, still good. And if I add another pi over 6, that's going to be too big. It's going to be beyond 2 pi. So basically what you're doing then is you're taking this possible solution list and you're just going to start listing them down until you reach your maximum of 2 pi. I know, kind of weird, huh? So as much as I hate that all real solutions, you know, like a plus and minus 2 pi n business, it is relatively useful, I suppose. Alright, this is the worksheet that's on the back. So in class we're going to be doing a lot of these together. Just remember, if you end up doing u-substitution, like we're going to have to do here, you're going to say u equals 2 theta, and you're going to find the all solutions one first. Let's see, I do have time to do this one. I'll do this one with you, okay? So let's set up -8 cosine of u, we'll call it, equals 4 square root of 2. If I'm going to solve, I'm going to have to divide by -8. And we get the cosine of u equals negative square root of 2 over 2. So, for all solutions, when is cosine negative square root of 2 over 2? That would be, let's see, quadrants 2 and 3. So that would be 3 pi over 4 plus or minus 2 pi n. And that would be at 5 pi over 4 plus or minus 2 pi n. But we don't even want that. We want to know what 2 theta is. Because that's what u was. Every time I say that, I feel like I'm saying weird English. So if I divide everything by 2, which you can think of it as multiplying by 1/2 if that's easier for your brain, I end up with theta equaling, let's see, that would be 3 pi over 8 plus pi n, and 5 pi over 8 plus pi n. Okay, so that's all solutions. But they only want between 0 and 2 pi. So what I'm going to do now is I'm going to start listing them. So starting with 3 pi over 8. 3 pi over 8 is good. If you add another 8 pi over 8 to that, which is 1 pi, that would be 11 pi over 8. So we're still good. If you add another group of 8 pi over 8, that'd be 19 over 8. That's too big, so stop listing. 5 pi over 8, good. Adding another group of 8 pi over 8, that'd be 13 pi over 8. Still good. If I add another group of 8, that's too big. So I think that's it. These 4 answers right here. So it's annoying because you do have to you feel like you're doing twice the work. You have to find the all solutions one, and then go back and find just the ones between 0 and 2 pi. Alright, I'm going to have to hang up the lesson there, guys. Class is about to start. But best of luck to you. Yes, this can be challenging, but you're going to see all different varieties on your test. We've got to become very skilled at solving all types of trig equations. Best of wishes to you.